Hello students, myself Chen, and today I am going to teach you substitution nucleophilic reaction. So what is substitution nucleophilic reaction? We will learn in this video. Okay, and this topic is very important to related to your exam like JEE, NEET. Okay, this topic is very important. So uh, nucleophilic substitution reaction. So nucleophilic substitution reaction is broadly classified into four portions. Okay, like SN1, SN2, SNAR, and SNI. So SN1 means substitution nucleophilic unimolecular. SN2 means substitution nucleophilic bimolecular. SNAR substitution nucleophilic aromatic. AR for aromatic. SNI substitution nucleophilic intramolecular. I for intramolecular. So in this video we will learn only SN1 and SN2. Okay, so what is SN1? SN1, as I mentioned, that SN1 is nothing but substitution nucleophilic unimolecular reaction. S for substitution, N for nucleophilic, and 1 stands for unimolecular reaction, right? Now, this is a general scheme. For example, Rx, okay, X is a leaving group, R is any alkyl group. So what you are doing, you are reacting this substrate with this nucleophile, and in presence of solvent what you are getting actually this nucleophile plus this nucleophile is added to the with R or react, or it may make a bond with this R and X leave as a leaving group. Okay, so this is nothing but your substrate or reactant, this is your product, this is your leaving group, and this is your nucleophile. Now, this is the general scheme of SN1 reaction, right? Now, for example, if you want to take an example, take an example. So, for example, this is tertiary butyl bromide. Okay. Now, what you are doing, you are in the this reaction is have two step. Okay, this reaction is going through via two step, like SN step 1. In step 1 what happened, that in presence of solvent, okay, in presence of solvent, that bromine will leave from the system, and you are generating what, you are generating a carbocation. But here is a chemistry that this bromine is leaving from the system. Okay, so this carbon and this bromine, this CBr bond is very weakening. Okay, as reaction is proceeding, what happened, this bond is becoming very weak. Okay, so we can represent this bond like this. Okay, bromine, this bond is cleaving, right? So this is nothing but your transition state 1, and we can represent the transition state in third bracket, and this sign is known as double dagger sign, right? Now what happened, after some time this bromine will kick out from the system, and you are generating this carbocation, okay, plus X minus. This is nothing but free ion pair. Okay, two ion is there, that's why it is known as free ion pair. Now this is the first step. Okay, in second step what happened, in second step that carbocation is there. Okay, and now what happened, this nucleophile is attacking over this carbocation, and what you are expecting, that these this nucleophile and this carbon make a bond. Okay, there is a bond between nucleophile and carbon, so the bond is forming, so it is present in initial state, so we can represent like this way. Okay, this is nothing but your transition state 2. Via this transition state 2, you are able to, when they make completely a bond, it will appear like this. This is nucleophile, right? This is your nothing but product. Okay, okay, so there is two step, right? This reaction is two step reaction. The first step is very slow, okay, and the second step is very fast. The slowest step of any reaction is known as RDS, that means rate determining step. Okay, this step is RDS. Okay, and why I am saying that this reaction is fast, this reaction or this step is fast, this step is slow. The question comes why? As you can see here that 8 electrons are there. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 bonded electrons are there. So complete octet. Okay. From here, as you are moving forward, it becomes incomplete. 1, 2, 3, 4, 5, 6. 6 electron. So incomplete octet. So from stability to going to the unstability. So that's why it is slow step. But from here to here, so here 6 electron, 6 electron. From here to here, 1, 2, 3, 4, 5, 6, 7, 8 bonded electron. So 8 electron. So there is complete octet. So from unstability is going to, from the unstability it is going towards stability. So that's why we can say that this is a fast step. Okay. Now I want to discuss the rate of reaction. Okay. So as you know that rate of reaction here in this case, this is the slowest step of this particular reaction, and this is nothing but your RDS, rate determining step. So the RDS step is depend only the concentration of the substrate. Here in the first step, there is no involvement of the nucleophile. So that's why we can say the rate of reaction is directly proportional to only the substrate concentration, right? So rate of reaction is equal to, if I want to replace this proportionality, I have to propose a proportionality constant, and this is your substrate. Now in substrate we have 1. So basically the rate of reaction is directly is equal to K into substrate concentration. The rate of reaction is only dependent on the substrate concentration. So this substrate, so it's like unimolecular. Okay, 1 is there, so that's why it is called unimolecular. And this reaction is hampered by only the concentration of the substrate. Okay, so now I want to discuss about the stereochemistry. So this is your stereochemistry of SN1 reaction. So for example, I have chosen this molecule to explain you the stereochemistry. So first what happened, that any leaving group, like this is nothing but your X. So first it will be removed from the system, and you are generating this molecule H, methyl and ethyl. Okay, and you can represent this in another way. How? Like for example, you can represent this like this way: methyl, hydrogen, and this is your ethyl. Okay, and here one lobe is there. Why I am drawing this lobe particularly? Okay, because if you know the hybridization rule, this is nothing but this carbon hybridization is 1 2 3, that means sp2, that means planar. Okay, so planar means what? Planar means it have two faces. If planarity means this is your planar compound, now it have two faces. One is, so the nucleophile can attack from the top face, also the nucleophile can attack from the bottom face. Okay, so there are two choices of this particular nucleophile. The nucleophile can come from the upper side or the top face, or the nucleophile can come from the bottom face also. Okay, now so if I want to show you that the nucleophile comes from the top side, also the nucleophile can come from the bottom side, because it's the planar species. Okay, at hybridization also is sp2. So what you are generating, if nucleophile is coming from the top phase, so this is become wedge, and this hydrogen comes in dash. And here also, if the nucleophile come from the bottom phase, the nucleophile comes in dash and the hydrogen comes in wedge. So for example, this nucleophile have higher priority. Like this nucleophile is nothing but OMe group. Okay, OMe. This nucleophile is nothing but OMe. So you can replace this OMe. Okay, OMe, and this is your nothing but OMe. Okay, so if you know the how to find R and S. I think you people know that how to find R and S. If you don't know, it's okay. Now, if the molecularity is high, if the atomic mass is high, then uh, the priority is going high. Okay. So, for example, this carbon is connected via oxygen. So, oxygen higher atomic number, so it goes 1. Okay. This ethyl, there is ethyl, it goes 2. Methyl, it goes 3. Hydrogen, it goes 4. Okay. Similarly, here it goes 1. It goes ethyl goes 2. This comes 3, and this comes 4. So you have to rotate now 1 to 2 to 3. So it anti-clockwise. That means S. Okay, so it is nothing but S configuration. So from here also 1 2 3. So it coming anti-clockwise S, but the fourth group is above the plane. So that's why it becomes R. So what we are getting is that 50% you are getting S and 50% you are getting R. So this is nothing but, this is called racemization. You are getting racemized product. So 50% you are getting R and 50% you are getting S. You are getting mixture of the products. So this is nothing but racemization. So clear? Now there is something called factors. How many factors can affect this particular reaction, SN1 reaction? The first factor is structure of the substrate. Okay, so as I mentioned that carbocation is forming in this particular reaction. So carbocation, whenever the carbocation is formed, if the carbocation is become stable, then that reaction is more facile. The rate of the reaction is very high. Okay, so the rate of reaction then directly proportional to the stability of carbocation. If the stability of the carbocation is high, then what happens? Then your rate of reaction is high. So as you know that 3 degree is more stable compared to 2 degree compared to 1 degree due to alpha hydrogen. Okay, due to alpha hydrogen. Okay, now as you can see here, I have taken these examples. For example, you are kicking out of these leaving groups like bromine and you are generating a carbocation here. Okay, this will make a carbocation, this will also make a carbocation, this will also make a carbocation, and this will also make a carbocation. Okay, okay, one methyl group is there. Okay, one methyl group is there. Okay, so 3 3. So you have to count the alpha hydrogen. How many hyperconjugation structure is there? Okay, 3 3 6 and 3 9. 9 alpha hydrogen is there. Here 3 3 6 alpha hydrogen. Here only 1 2. Okay, so the 2 alpha hydrogen is there, C and H3 plus. There is no alpha hydrogen. Alpha hydrogen means that this carbocation should connect it through a alpha carbon, and that alpha carbon contains some hydrogen that known as alpha hydrogen, right? So this is like that. Okay, 9 alpha hydrogen, 6 2, and then there is nothing but 0. So stability becomes this. Okay, here similar thing, kick out the chlorine and make a positive charge. Kick out the chlorine, make a positive charge. Kick out the chlorine, make a positive charge. So nitrogen, it has some lone pair. That lone pair is delocalizing here. Oxygen, delocalizing, but here no delocalization is there. Okay, so the electronegativity here, electronegativity factor plays an important role. Like in this case, nitrogen is less electronegative compared to oxygen. So oxygen is more electronegative compared to nitrogen. So that's why it will not so easily delocalizing its electron. So that's why the stability becomes this. Okay, why here it is the least? Because it have only the plus-i effect, but here plus-r is there. Okay, okay. Now coming to the second point, concentration and reactivity of nucleophile. Okay, as I mentioned that rate of reaction is directly proportional to the only of the substrate. It is not depending on the concentration of nucleophile. So that's why I have written here that is unaffected. But weak and neutral, if weak and neutral nucleophile is there, the reaction is fast. Like it favors SN1 reaction. Okay, like you have alcohol and you have this RO minus. Okay, this will favor SN1, but this will favor SN2 because it's a strong nucleophile. So that's why it will favor SN2, but this alcohol is favoring SN1 reaction, right? Okay, now coming to the solvent portion, that how What was the solvent you need? That your polar protic solvent. Why polar protic particularly? Polar protic, so for example, you have take this example, Rx in presence of water, it will kick out from the system and you are generating this. Okay, so cation as well as a counterpart X minus. Okay, this cation, as you can see here, this is cation R plus and this is your X minus part, that is your leaving group. So the cation and the counterpart both are stabilized in polar protic solvent. Okay, and polar protic means polar, it have some electronegativity difference, so that's why we are saying polar. Protic means it is connected through a electronegative atom like oxygen, and this hydrogen is connected through an electronegative atom, that's why it is called protic. Okay, so polar protic. So these cation and counterpart is stabilizing, that's why we are choosing polar protic solvent for in case of SN1 reaction. So here this is your DMF dimethyl formamide. This is polar. C double bond C double bond O is there, so that's why it is polar. But here no hydrogen is there, that is connected through a electronegative atom. So that's why it is polar aprotic. Okay, this is your non-polar. CCl4 is also non-polar. N-hexane is also non-polar. Okay, alcohol. So this is polar, but one hydrogen is connected through this oxygen, so protic, polar protic. Also, acid is also polar protic. Now, this is the last factor, which is nature of leaving group. So, in this case, so you can kick out X from the system, and you are generating this free ion pair, right? Now, if the X minus becomes stable after removing, if it is if so if this bond is break, then it will become X minus. If X minus will become stable, then this free ion pair will form. If X minus will not stable, then X minus will again attack and it will regenerate this Rx, right? So if this X minus is become stable, then it have some high stability. If it is have high stability, then the leaving group ability is high. Okay, that's what I am saying. So high stability, if X minus have stability high, then leaving group ability is high. Okay, so as you know that between fluorine, chlorine, bromine and iodine has more size. Okay, so it have more space to delocalize this negative charge compared to bromine, compared to chlorine, compared to fluorine. So here size effect comes. Okay, here size effect comes. Now I just want to discuss some of the examples which is relevant to your exam. So for example, first one. So as you can see here, polar protic solvent. So kick out the so what was asking in that question, you have to write down the product. Okay, so first kick out the bromine from the system. So you are generating nothing but carbon. This is methyl, now this is methyl and CH2 plus. So here one trick is there, not trick, that is chemistry is there. So this is your 1 degree carbocation, right? Now here one process is called shifting. Okay, this methyl is shift here or migrating, that known as 1 to migration. This migration is happening. So after this migration, so you are generating carbocation here, right? CH2 CH3. Now this carbocation is 3 degree, and as I mentioned that 3 degree carbocation is more stable compared to your 1 degree, so that will form majorly. Okay, after that water will attack here, water will come and attack, and you are generating methyl carbon OH H methyl CH2 CH3. Okay, this is positive charge. Now this 2 electron is coming here to neutralize this oxygen. So your product is COH CH2 CH3. This is your methyl, this is your methyl. Okay, this is your final product. Okay, so first question is done. Now coming to the second question, that you have to tell them that which is more stable and which will undergo the SN1 in a faster rate. Okay, So kick out the X, generate a carbocation. Kick out the X, generate a carbocation. So 3 3 6 3 9, 9 alpha hydrogen. Here 0 alpha, because this carbon, this is alpha carbon. Now this carbon, there is no alpha hydrogen. So that's why 0 alpha hydrogen. That means stability is high. So this will undergo SN1 in a faster rate compared to this. Okay, this is benzyl radical. Okay, now here the same question is asked. You have to write down the product. Okay, so bromine will kick out from the system first. What you are generating a carbocation here. Okay, this is your tertiary, sorry, 3 degree carbocation. Now this methanol will attack here. This is nothing but your methanol, and what will form here is methyl and OMe. For example, here ethanol is there. Okay, so you have to write OET. Okay, ACOH is there. Okay, you have to write OAC like that. Okay, so now in this question, that is the next question, you have to compare the stability or which will undergo the SN1 as a faster rate. So same thing, you have to kick out the chlorine. Whenever the SN1 is coming, you have to kick out the leaving group. After that, you have to check the stability. Okay, if it is stable, then it will undergo a faster reaction in SN1. Or if carbocation is not stable, then it will not undergo SN1 reaction. Right? This is as simple as that. So this is cation. Now this is nothing but your cation. Okay, there is cation. So resonance stabilized, plus R. Okay, here one plus R and here only plus I. Here only plus I and plus I. So from the general organic chemistry knowledge, plus R effect is more predominant compared to plus I. So that's why the stability is like this. Okay. Now in this case, you have to write down the product again. So first oxygen lone pair is there, acid is there. So it will take acidic proton from the HCl, and this will generate OH2 positive charge. Now this is OH2 positive charge is a good leaving group. Okay, so it will leave from the system. So first you have to make a good leaving group. So it will generate a carbocation. Okay, so as you can see here, this is a 2 degree carbocation, but here one hydrogen is there. That hydrogen is shifted here. You may ask me that why this methyl is not shifting here, why particularly hydrogen? That is nothing but migratory amplitude. The hydrogen migratory amplitude or hydride migratory amplitude is high compared to your methyl migration. So that's why hydrogen is migrating here and you are generating this carbocation here. Okay, so this is tertiary carbocation, and now this Cl minus will attack here and you are generating your product. Okay, methyl and Cl. Okay, as simple as that. Now here again you have to write the stability. Okay, or which will undergo as a faster rate reaction. So here kick out the bromine. Okay, from all the system you have to kick out the bromine first. Bromine. Okay, so positive charge, and positive charge. 9 alpha hydrogen, 6 alpha hydrogen, 3 alpha hydrogen, and here 0 alpha hydrogen. So basically stability order, this one greater than this one, greater than this one, greater than this one. Okay, now in these two cases, kick out the chlorine. Okay, this is positive charge. Now here kick out the chlorine, this is positive charge. Now this oxygen can delocalize its lone pair here, but here it is not possible. So that's why the stability order this greater than this. Okay, now in this case, the similar thing, kick out the chlorine, make a positive charge, kick out the chlorine, make a positive charge. With the 3 phenyl ring, it is resonance stabilized, plus R effect with 3 ring. But only here, plus R effect is there, but only with a double bond. So here the effect is high, plus R effect is high. So that's why the stability is like this. Here, the chlorine, same substrate, but they change the leaving group. Like they put chlorine and one in this case bromine. So as you know, the bromine, like leaving group ability, so bromine have much more leaving group ability. So that's why this will kick out, okay, and make a positive charge there. So you can say here that this will undergo as a faster rate reaction because bromine is there, right? compared to chlorine. So there comes leaving group ability. Okay, leaving group ability. Now in this case, you may kick out X from here and make a carbocation, but this is very unstable. According to Brett's rule, in the bridged position, carbocation will never form. Okay, according to Brett's rule, there was a rule. That rule says that there is no formation of carbocation in this particular bridged position. So that's why it is not possible, right? Now in this case, it is possible because it is not bridged position. So X, kick out the X, make a carbocation. So which will undergo in SN1 reaction? This will undergo SN1 reaction, but this will not. Okay. So with this, thank you, and I am ending my session.